Alright, let's finish this up. So we're going to talk about osmosis first, and then we will talk about colloids. So osmosis is something that you knew about if you were a kid around the time that I was, because there was the Osmosis Jones movie, which some of you might remember. Unfortunately, unless I am misremembering, they don't actually ever talk about osmosis in that movie. It just sounds like a cool sciencey word to go along with Jones, I guess. I don't know. Maybe they did, and I just don't remember. Like I said, I was relatively young when that came out, and I only saw it once. But anyway, scientifically, what osmosis is, it's the process by which a pure solvent moves through a semi-permeable membrane towards a solution. So more specifically, in a little bit more detail, what's happening here, just as an example, if we have a U-shaped container like this, so some kind of a tube in a U shape like this, and at the bottom there is what's called a semi-permeable membrane, and what that means is the solvent can move back and forth through the membrane, but the solute cannot. So the solute is stuck on this side of the tube, but the solvent can go wherever it wants. If you start with equal volumes on both sides of the tube, what will happen is the solvent molecules will want to be over here with the solute. Again, there's positive interactions, intermolecular forces between the solute and the solvent, and so the solute molecules are like, ooh, look at those solute molecules over there. I want to go over there. And so the solvent molecules will travel from one side of the tube to the other, to the point where gravity says, okay, that's enough. No more of you. No more moving over. Because remember, gravity is trying to equalize the height on both sides. If you ever put liquid into a tube of something like a bent straw or anything like that that's kind of in that shape, it equalizes to the two sides as long as both sides are open. The liquid on both sides of the tube will be equal in height, and that's just because of gravity. Gravity wants them to be equal. But the positive interactions, those intermolecular forces between the solvent and the solute, will actually overcome gravity to a point, to a certain point, and so that is the height at which the solvent will no longer push upwards. So if you wanted to push the solvent back, to force it back to the other side of the semi-permeable membrane, it would take some effort to do that. Because again, the solvent wants to be on that side, so it's not going to go willingly. The amount of pressure that it takes to push it back is the osmotic pressure. And then again, the osmotic pressure is the amount of pressure it takes to equalize the height on both sides, to overcome those intermolecular forces wanting the solvent to be on the side there with the solute. Interestingly, the osmotic pressure obeys a law that is very similar to the ideal gas law. And really it's actually identical to the ideal gas law. We just kind of write it differently. So the osmotic pressure, which is normally written as a capital Greek letter pi, that's what that is. I know it kind of looks like Greek or the Roman numeral 2, but that is the capital pi. So that is equal to the molarity, which is just the number of moles divided by the volume, times RT. And R and T are the same as in the ideal gas law. So it's the gas constant and the temperature in Kelvin. So it's very, very similar to the ideal gas law. Really the only difference is you're using it to describe a solution instead of describing a gas. So let's look at a real quick example here with this. This asks us to find what is the osmotic pressure in atmospheres of a 0.3 molar solution of glucose in water that is used for intravenous infusion at body temperature, which is 37 degrees C. So why don't you go ahead and try this one out on your own. It's not too crazy difficult. It really is mostly just a plug and chug. You just have to kind of watch the units and make sure that you have the correct units when you're plugging things in to your calculator. So go ahead and give this one a shot and pause the video. Alright, so we're trying to find the osmotic pressure, and we know that is equal to the molarity times RT. Now, almost all those things are given to us in the question. Technically speaking, R is not given to us in the question, but we know, because we remember from Gen Chem 1, and I guess I'll go with the, I learned 0.08206. Most modern books use 0.0821, so we'll go with that. Liter atmospheres per mole K. The molarity, just straight up given to us, so there's no need to calculate that. T is also given to us, but it must be in Kelvin, and we were given the temperature in Celsius. Thankfully, it is not difficult to switch. Just add 273, so the temperature in Kelvin is 310. So that is your temperature, or close to it anyway, in Kelvin, 310. Okay, so we have everything we need. So the pressure is going to be 0.3 molar times 0.0821 liter atmospheres per mole K times 310 Kelvin. So the Kelvin is going to cancel out here, and the moles per liter that is inside the molarity is going to cancel out with the liters and moles there. So those are going to go away, leaving us with atmospheres, which is good because that's what we want. So if we do the math, 0.3 times 0.0821 times 310 gives us 7.6, we'll say 4, we'll round that up, 7.64 atmospheres. All right, so that is a lot of pressure. That's actually a lot of pressure. I'm actually kind of second-guessing myself, making sure that I plugged everything in correctly, and I believe I did. That is a lot of pressure. But osmosis is a strong force as well. So this is the pressure that you want, as it says here, when you're putting an IV into someone. You want to have some amount of solute in that IV, whether it is saline or whether it is a glucose IV or whatever it is. You need something in that IV. Otherwise, what happens if you have nothing other than water in the IV? You will have that would be a hypoosmotic solution at that point, because what happens if you just inject pure water into your blood veins, the pure water that goes into the blood sees, or really, again, I'm kind of pretending like it's sentient and has a personality, but it essentially it is attracted to the solute molecules inside of the blood cells, because it doesn't have anything. It's just pure water. It has no solute if you're just injecting pure water. And so it can sense, in a sense, it can feel, it is attracted to the solute molecules inside of the blood cells, and so it will just push its way into that blood cell, causing the blood cell to expand to the point where it is damaged or killed, to where just there's too much solvent in the blood cells. Now the opposite is true if you put too much solute in. So if instead of giving the proper amount of saline or whatever it is, the proper concentration, if you have too concentrated of a solution, then you have all these new solute molecules directly introduced into the bloodstream. And so the water that's in the blood cells senses the higher concentration of solute outside of the blood cells and says, ooh, all those solute molecules, look at those. I want to go dissolve those things. And so all the water leaves the blood cells, leaving them all shriveled up, like in a hyperosmotic solution. So all the water leaves the blood cells to go chase after those other solute molecules. And so you kill the blood cells in that sense as well. It's only when you have just the right amount of solute that you get an isoosmotic solution here, where the concentration of solute that you're putting into the blood is the same as the concentration in the blood cells, and so there's no movement of water in one direction or the other. If you get this wrong, you will kill your patient. It has happened before, and I'm sure it'll happen again. This is why the IV drips are saline, not water. Why they have the 0.9% sodium chloride. You know, some people think, why are you putting salt water into people? Like, you don't drink salt water. Why would you put it in your blood veins? Well, it's because when you drink water, your body takes what it needs and sends the rest out. If you're directly injecting it into your veins, that is a whole different matter, because your body is not processing it at that point. You are, in a sense, manually inserting. So your body can, doesn't like drinking salt water, but if you're going to be putting water directly into your blood veins, it needs a certain amount of solute, otherwise bad stuff happens. Alright, last quick thing here, colloids. This is a different type of solution where the particles are larger than typical molecules, but small enough that they can still stay in solution. The gravity doesn't immediately, anyway, pull them out of solution. It does eventually pull them out of solution, but not like very large particles like water droplets. There are tons of different kinds of colloids. Some of them you are familiar with because you interact with them all the time, and other ones you're not quite so familiar with. But things like fog and smoke, those are colloids because there are tiny little particles in the air that are bigger than just typical gas molecules like nitrogen or oxygen molecules. They're much bigger than those, but they're much smaller than a water droplet or a piece of ash or something like that quickly falls out of the air. The main difference between the fog and the smoke is just the thing that is dispersed. So in fog you have little tiny liquid droplets dispersed. Smoke is little tiny solid droplets dispersed. Whipped cream is also a colloid. You have tiny little bits of gas dispersed in a liquid. Milk and paint are also colloids. So in paint, for example, you have little tiny pieces of solid that are immersed in a liquid. That's what gives the paint its colors, little tiny flecks of solid. And then marshmallows, butter, these are colloids where the main component is a solid. So you have marshmallow, for example. If you ever made homemade marshmallow, or actually I should say if you have not made homemade marshmallow, I would encourage you to do it at least once. It is pretty messy. Um, and you know, it's kind of hard to clean up afterwards, but they're good. Good stuff. Homemade marshmallows. And the way that you make homemade marshmallows, and you really need an electric, uh, like a KitchenAid or something like that. If you don't have one, I would not encourage you to do this by hand. Um, you, I don't think you'll be able to do it by hand. It's just a lot of work. You essentially just beat the gas into the sugar mixture. So you have this really thick, sugary stuff, and you just beat it and beat it and beat it and beat it and beat it, and you just physically incorporate gas into the liquid while it's still hot. And so as it's cooling down and starts to solidify more and more, the gas gets trapped in there, and that's actually what gives it its, you know, its poofy, airy type texture. Is just little bits of gas that you have trapped inside of there. It's kind of a similar thing with butter, except you have a liquid trapped in there. So if you've ever churned butter, this is why you have to, you know, just constantly churning and churning. It's kind of the same thing as the marshmallow, where you're beating it and forcing the things to mix together. The last one there, most jewels, like ruby, for example, and things like that. This is actually a solid in solid colloid. Rubies, for example, if I remember correctly, are actually aluminum oxide with a very specific crystal structure with little tiny bits of a different material, and I don't remember what the other material is. But if I remember correctly, the only difference between emerald, sapphire, and ruby is that little bit that is dispersed in it. There's just essentially a contaminant that gives those three different jewels their color. The vast majority of the chemical structure is actually exactly the same between them. It's just the contaminant that makes them a different color. Now you can double check me on to make sure that I have my jewels correct there, but I know there are multiple very well known jewels that, chemically speaking, are nearly identical. They look very different, and the only reason they look different is because of that little bit of contaminant. So there's just a few examples there of some different colloids, and the light coming in and being dispersed in the fog. Vinaigrettes are also considered a colloid. When you shake it up, they stay mixed together because of a surfactant that exists in there that keeps them together. Alright, that is the end of this chapter. Make sure that if you haven't already, you get started on the homework soon, so you can get those done while it's still fresh in your mind. And if you have questions, feel free to email me, or we can talk the next time we meet. Good luck.